So, hello everyone, I'm Marina Cagliari, I'm a postdoc at LabTH in Annecy, France, and today I'm going to talk about a few works I've done related to primordial non-Gaussianities. But before saying what I did, let's ask ourselves, I guess many in the room already knows why we want to measure primordial non-Gaussianities, in particular local types, but let me give you a short reminder. Primordial non-Gaussianities are important because they can gives us an idea of what happened during inflation, in particular about inflation dynamics. And inflation, we know, is a key ingredient in the lambda CDM model, in the CDM model in general. It gives us, it solves problems and also gives us prediction. And so primordial non-Gaussianities can give us an insight of the dynamic of inflation. In particular, the primordial non-Gaussianities of local type can help us distinguish between single and multi-field inflation models. And if we were able to get to this magic number here of an error of about 1, we would be able to either with a detection rule out single field inflation models, or with a non-detection, we would still be able to constrain multi-field models. So right now, the state of the art, like the best measurement we have are from the 3-point function of the CMB with an error of order of 1. But LSS is getting there. With latest disease results, we have an error of the order of about 1, and the potentiality of LSS is much larger, I think, in that sense, with respect to CMB, as due to the three-dimensional nature of this measurement, we can access to much larger modes. So what are currently the data that we have available? We heard a lot about it, well, already this morning about DESI and also in the last week for the one around. So the new generation data are actually already here. DR1 DESI is already out. The measurement for the BA of DR2 are out as well. And also Euclid is coming. Probably the data will be in a year and a half, maybe a bit more. Not sure, but we can still use all generation surveys to try to understand how to extract the most out of this new generation. So in the first part of the talk, I'm going to talk about some results that we got from the analysis of the quasar-IBOS DR16 sample. So this is, let's say, a much smaller survey than what we are currently dealing with, but it can still be quite interesting. So how does FNL affect the large-scale structure? We can actually measure local FNL directly from the power spectrum, as it induces a coupling between large and short small scales, which produce a scale-dependent bias. And so we can see in the power spectrum itself a deviation at very large scales. To measure this, what we did was not using, let's say, the standard FKP power spectrum, but we used optimal weights to make these measurements. And the importance of this is because if we consider the N of Z of a survey, then the signal of FNL is constant with redshift as a primordial signal, while the gravitational signal, we know it increases with lower redshift. And so we want to upweight where the signal-to-noise ratio is higher. We use these optimal weights that indeed upweights the higher redshift. Here you can see this, the shape of these weights with respect to the FKP for two different values of P in the universal relation. Let's say, and here you can see the results from this work for the one-dimensional posterior distribution. We can see that the optimal weights in both cases with respect to the FKP, they debias the results, and also it makes the constraint tighter, in particular 11% for P equal to 1 and 29%, so almost 30% for P equal 1.6, pointing in the direction that this choice of P should be better for the quasar sample. Now the question is, can we do better? The answer is yes, in a few different ways. Either we go for larger surveys, as we are also currently doing, like DESI. We know the results of DESI, like we will try to do with Euclid. But then here the issue is that we have a large-scale systematic that we have to deal with. At the same time, we can also try to combine the two-point function with higher order statistic, for example, the three-point function or higher, and try to get more information from the same data that we had. And indeed, for this second work, we combine the optimal power spectrum, so the two-point function of the same dataset with the bispectrum. We use a three-level model for both of them. And here you can see what we got. Indeed, we have an improvement for both values of P, 13% improvement for the P equal to 1, and then 10% for P equal to 1.6. Now, if we want to get better, we could try to add the 4-point function, 5, and then go on. But clearly, this can be extremely difficult at the modeling level, or in general, also at the measurement level. So one thing we are all thinking about, I think at least a bit in the room, or I have an opinion, is field level analysis. A possible way to do field level analysis is to use machine learning. But then this is plagued by memory issues, and also to do field level analysis with machine learning, we have to run a lot of simulation, which can be difficult by itself. So the idea of this last work that I'm going to present is, can we take, for example, a larger simulation for now, divided it in sub-little patches, and then analyze each one of them, so at a field level, and get some summary statistic for the small scales. And then for the whole simulation, we can still measure the power spectrum and the bispectrum, for example, which will give us some information about the larger scales, and then combine these together. So what we did was Fisher information studies of this summary statistic that comprise the power spectrum, bispectrum, and this patch summary statistic. We did it for simulated boxes at Redshift 1. We also did it for other Redshift, but I'm going to present the results at Redshift 1. To do this analysis, we used the FOF Halo catalogs for the Quixote PNG, and then we divided all the boxes in 64 sub-patches, which are resolution then on this grid of 8 megaparsec over H. And here you can see the improvement we can observe for two different mass cuts in the halos. The first thing you can notice is that when we add the patch information, we get always tighter constraint, which is good. Something is at least seems to be working. And also, another thing that is interesting is that the power spectrum plus patches is better than the power spectrum plus bispectrum, pointing in the direction that probably we're getting higher order statistic information. But again, if we add the bispectrum, we get a slightly better constraint, showing that the bispectrum at large scales it's still bringing in information which the patches cannot access to, as they are small. Another thing that is interesting is that for the higher mass cut, the relative improvement is larger, showing that this seems to be working more for more biased tracer, which could be, for example, quasar in real life. And finally, that if we take, let's say, we want a given constraint, with this addition of patches, we can get to it with a much lower Kmax in our summary statistic that we are combining. So here are my conclusion. I presented you different ways to try to improve constraint from LSS. First of all, the optimal power spectrum for the first analysis, which can improve about 29% up to 30%. Combining then optimal power spectrum and bispectrum can improve up to almost 40%, which is equivalent, let's say, in almost 3-time volume survey, and also it shows that possibly combining small-scale field level analysis can improve. What about the future? Currently, I'm working with ASDE on the local PLG analysis for the Euclid DR1, first power spectrum, and then maybe power spectrum and bispectrum. And with this, I thank you for your attention.
When you were showing this power spectrum plus patches, was the Kmax just for the power spectrum by spectrum, or was it also the Kmax of the patches?
No, so the patch we keep always the same grid size, while here what I'm showing is for just the power spectrum and bispectrum. So for all of them, also I don't combine, let's say, different cuts for the power spectrum and my spectrum. So it's
why is there so much improvement as a function of Kmax, given that this Kmax is so high?
I'm not sure. I would say like this is just let's say the feature information, so I'm not adding any model, so that is what you would expect from increasing the Kmax just with the feature information analysis. Then at the same time is the issue is that can we model up to here, for example, power spectrum and bispectrum, and we have heard a lot of the difficulties already to get to.
You tried to maybe compare to what model tracer would do, because it would be similar. Would there be any improvements in this machine learning stuff if you did a model tracer?
I'm not sure. I admit, like for now, it's still like on the halos of the simulation. It may be possible, and it could be an interesting comparison, definitely.
Very fast is that there you are not very short. One of that for low mass halos, you're actually getting information.
I know. Okay, so if that was the question, sorry, I didn't. I misunderstood and okay. But no, yeah, I would say so as well.
Large scale modulations. When you add these patches to your analysis, is there any information being added to the patch?
Sorry, there was the noise exactly when you were asking the. No, there is currently there is not information of the patches. So like we analyze the network will analyze each one of them, take a summary statistic, which will be the value of FNL, and then average over them. And in this case, it's not using any information. In the say precursive paper of this work, which is just for lambda CDM, I know that they are also overlapping the patches. So in this way, you're clearly also taking some information of that. But for this, we didn't have the time to implement that as well. So here is not. Yeah, I would say definitely the squeeze triangle, but then also like, for example, then indeed that's, I guess, the reason why when we add also the bispectrum is still doing something, because you will have like the most squeeze triangle that you cannot access to with the patch. But then no more.
Okay, let's thank Marina.